Hello, everyone, and welcome to our event today on behalf of the student branch of the IEEE at the University of Birmingham. I'd like to welcome you to this event. Professor Xiaoping is going to be giving us a brief introduction, and then we'll welcome our speaker, Dr. Grazia Todeschini.
Good afternoon, everyone. We have the great pleasure to have this seminar on power quality in modern electricity system with a large penetration of power electronics-based devices. The topic itself is very important to the future low-carbon electricity system. Today's event is organized by IEEE University of Birmingham branch, student branch, and sponsored by Birmingham University Energy Institute. My name is Xiaoping Zhang, Professor of Electric Power System. I also a fellow member of IEEE. So it's my great pleasure to introduce these events and also say a few words about IEEE, in particular IEEE Power and Energy Society. If you are members of IEEE or student member of IEEE, probably you already got a lot of ideas about IEEE and their resources, activities, and so on. If you have not been a member of IEEE, probably it's worth considering joining this important professional organization. The IEEE actually, they publish probably most influential magazine and section journals. The most of the influential papers, I think, published in these journals. Another very important aspect is IEEE organize all sorts of conferences, workshops, seminars, like today's events regularly. So if you are a member, you're going to have more opportunity to join broad conference, webinar, and so on. Also, IEEE Power and Energy Society, they have a resource center. Quite some resources are available to IEEE member, particularly IEEE Power and Energy Society members. Certainly, there are also some technical activities I want to mention, like IEEE working group. If you have a particular interest, for instance, power quality, there are related working group in IEEE societies. So if you are a member, you can join those activities very easily and get into the discussion and even give significant contribution. Certainly, I have the great pleasure to welcome you join today's events. Hope through today's event, you're going to learn more about the power quality and their importance in our modern electricity system. Thank you very much.
Thank you, Professor. And thank you to all of you who have joined us. A few points of housekeeping before we start. Today's session will have a presentation to kick the session off. And then at the end, we'll have question and answers from the audience. All the question and answers today will be done through the Q&A session, not the chat function. So as the presentation is moving along, do feel free to type in your question and we'll answer all those questions either orally or in text at the end of the presentation. So it's with my great pleasure that I'd like to introduce our speaker today, Dr. Grazia Todeschini. Grazia received her PhD in electrical computer engineering from Worcester Polytechnic Institute in Massachusetts in the US, and has held various roles from senior consultancy to power studies engineer at General Electric, and became a senior lecturer at Swansea in 2016. So she has quite the diverse background, as well as her research interests, which lie in power quality, as we'll see from the presentation today. She's a senior IEEE member and fellow of the Higher Education Academy, and we very much look forward to your presentation. So with that, the floor is yours, and we look forward to it.
Thank you very much for the introduction from both Professor Zhang and Daniel. And thank you for the opportunity to give this webinar today. I will start, with a little bit of overview of my professional experience. Even if there has been some introduction, I just want to add maybe a couple of words, just to maybe provide some more motivation of my current work and research. Then I will talk about power quality research in general, and talking about the opportunities for this topic. And then I will describe some of the research projects I'm currently involved. As has been already mentioned, I took my PhD at Worcester Polytechnic Institute, and this Worcester is not in the Midlands, it's in Massachusetts. And that's where my interest for power quality started. I had the honor to work with Professor Alexander Emanuel, who is one of the experts in this area. And with him, I started to become passionate about this topic. I moved to the power industry after my PhD, mostly because during my studies, I didn't have the opportunity to work with industry or on practical application. And I felt that was a big gap in my background. So I spent about 3 years working for Enernex and about 3 other years working with the GE. And these two opportunities allowed me to develop some skills, such as working in the hardware in the loop lab. We used RTDS at the time. Or also I had the opportunity to go on the field, particularly some wind plants in the United States, and take power quality measurements. However, my heart has always been in academia, so after these experiences, I felt it was the time for me to go back to research and teaching, and that's when I joined Swansea University. At Swansea, I'm currently PI of 2 research projects. One is funded by Ofgem, and one is funded by EPSRC, and I will discuss these 2 projects more in detail later on. I'm also co-I of 2 ERDF funded research projects. ERDF is the European Region Development Fund, and these projects are going to finish in December 2020. As Professor Zhang mentioned earlier, IEEE has a power quality subcommittee that is very active, and I'm involved with a few working groups. And in fact, after this meeting, we have a meeting to discuss IEEE Standard 519. And then I'm also teaching modules related to power engineering and electrical machines. So if I have to summarize my research in a sentence, this is the one shown here in the slide. My research is focused on studying the effect of power electronics devices on power quality of the electrical grid. So I thought I would spend some words about power quality in a general sense, just because I think the attendees may have a diverse background and perhaps not everyone is familiar with the topic. So in an ideal power system, voltage and currents waveform are sinusoidal at fundamental frequency. So this is an assumption that we make quite often, both when teaching or learning, and also in the practice, because most of the time we can approximate the power system in this way, and it works. However, in the practice, there are disturbances, various types of disturbances that may not be detrimental, and most of the time are not detrimental, but they change the shape of current and voltage waveforms. So IEEE standard 61000 defines power quality as the ability of an equipment or system to function satisfactorily in its electromagnetic environment without introducing intolerable electromagnetic disturbances to anything in that environment. So what this means is that any device that is connected to the system is subject to existing disturbances. So disturbances generated in the system, but itself is a source of disturbance. So the point of power quality is to ensure that these disturbances are within acceptable limits. More in general, power quality can be studied in the framework of electromagnetic compatibility, and this can be explained quite easily using this graph. So in this figure, the top part here in this diagram shows the electrical environment, and the lower part is the load. But the electrical environment here is shown as an equivalent, but really it includes loads and any type of devices. So in this case, we can assume that there is going to be a certain disturbance from the environment. So disturbance could be anything, could be harmonics, or could be voltage variations. So it's not limited to a specific type. And the disturbance is generally not fixed in time. So we have on the x-axis the disturbance level, on the y-axis the probability density, and we can assume that the disturbance will be represented by a type of probability distribution, in this case a Gaussian. I will explain in the next slide what this CL means. Just, for now, we just keep it here as reference. On the other side, the equipment possesses an immunity. That means an ability to withstand the disturbances. And again, the equipment immunity can be approximated with the Gaussian, because the equipment is built with certain tolerances, and because there are various factors that change immunity in time, such as aging or other type of variations. So what is the point then of these two graphs? Well, electromagnetic compatibility essentially means that the system and the equipment is designed in such a way that we minimize the interference. So system disturbance is kept below a certain level, and equipment immunity has to be above a certain level. So this level is essentially provided by this vertical line. So CL that I shown previously is the compatibility level, and this is defined as a reference level for coordination in the setting of emission and immunity. Just a few other things to note in this graph. The emission of individual sources are generally small, but then they combine and they provide the system disturbance. Planning levels are the levels of disturbance where the system is expected to operate. And immunity level are the minimum immunity levels for the equipment. So you can see that in the practice, the immunity is above the test level and the disturbance is below the planning level. The last thing I just want to emphasize in this graph is that system disturbance and equipment immunity are defined allowing a 5% probability of overlap, because it's not practical to define a system that is 100% resilient. So we allow, in general, this 5% probability here. I also want to bring to your attention this other standard from IEEE that classifies PQ disturbances. And you can see that the classification includes quite a lot of categories and actually continues on the next page. And the main differences between transient and steady state disturbances. And then within these two main groups, there are many other types of events that are generally defined by the duration. So you can see that essentially this table starts with the fastest events and then continues with longer durations. So we get then to events such as unbalance and voltage distortion that are generally steady state because they last several cycles or minutes or even longer. Just want to show an example, just to give a little bit of visual on what I'm talking about. So one example of transient disturbance is capacitor switching. So this is quite a typical waveform. At the top, you have voltage, at the bottom, current. You can see current is slightly distorted at the beginning, and the capacitor is clearly switched in at this time. So you will see a transient generally when capacitors are switched in, not when they're switched out. Obviously, when they're switched out, the current may decrease, the system current. But you won't see as much of a transient. The severity of the transient depends on the point of wave, but this is quite a typical waveform. Obviously, you can note that while the voltage disturbance is relatively minor in this case, this current peak is quite high. So the system needs to be designed to withstand this type of disturbances, and that's where the immunity level is defined. And that's the basic of what is called insulation coordination. Another type of event is harmonics. Harmonics, as I said, are generally considered steady state events. So this is a waveform recorded in a wind plant. And you may think by looking at this waveform, this is current waveform, that this is a fundamental with some type of modulation waveform overlapped. But actually, when we did the FFT, we figured out that really this is mostly a fifth harmonic. So clearly there was some problem with the inverter control for that particular operating condition. In this case, the fundamental current is at 60 Hertz because this waveform was recorded in the United States. So that's corresponding to the fifth harmonic here. And then you can see a few other components. So why we worry about this? What are the consequences of disturbances? Well, in general, low level of disturbances don't create issues and they're well tolerated. With increasing levels of disturbances, we can have various detrimental effects. Some of these effects are not visible or obvious. For example, reduced efficiency, aging of equipment, errors in metering. So they may last for some time before you find out there is a problem. Other more severe effects could be interruption in manufacturing processing. For example, if a protection trips and the plant is taken out of service, or even worse, if the protection doesn't trip, the equipment may be damaged. So what are the research opportunities in power quality? Well, power quality is a topic as old as power systems. So the first power quality disturbances were detected in the late 1800s. So as soon as the first power system started to develop. And then power quality was a very active research area for some time, I would say in the second half of the 1900s. But then because power systems were mostly established by the end of the century, and most of the power quality sources have been identified, standards were in place, this area became a little bit obsolete. However, recently, there are new concerns in power quality related to the modernization of the electricity grid. And in particular, as the title of this presentation says, because of the connection of power electronic-based devices. One obvious effect is the impact of renewable energy sources or other power electronic-based devices on voltage levels, so voltage profiles in the system and harmonics. Another concern is related to voltage imbalance, mostly due to presence of single-phase equipment, such as the solar panels of EVs that are connected and disconnected at different points on time. Flicker is another concern. I'm not a big fan of this concept, but it comes up quite a lot when dealing with power quality research, so I just thought to mention it. And then there is a new trend in power quality that's related to superharmonics. And superharmonics are essentially harmonic currents with frequencies in the order of a few kilohertz. So while traditional power quality research or power quality standards limit the harmonic level of concern to the 50th order, superharmonic look into much higher frequency range. My research within all this context deals mostly with harmonic modeling and mitigation. Part of the reason is because I think there is quite a lot to do in this area, and I think it's just there are a lot of opportunities, and because it's really the topic I started to study during my PhD. So I always, had the passion, as I said earlier, for this area. There are many challenges here. I mean, I could spend a lot of time discussing the challenges, but for the sake of time, I just will be very brief. One challenge is regard the modeling of harmonic sources and their variability in time. So while in the past, in, let's say, traditional power systems or before distributed generation was deployed, the sources of harmonics were well known and were generally centralized. So typically, manufacturing plants, in particular steel plants, were known to be harmonic sources. So it was relatively easy to model their distortion because it was known and the variation in time was known. Now, with power electronic-based devices, it's much more challenging to model harmonics because these sources are spread, so they're not localized, because there are many manufacturers, each one implemented different controls, and because the variability in time is more random. So this problem is not only related to renewable energy sources or EVs, but in general consumer electronics or any other device that can be connected and disconnected by customer at the distribution system level. So the challenging of modeling harmonic, I think, is very important. Another topic is calculate summation of harmonics. So given that there are so many sources, most of the time it's not practical to model every individual device, just because the simulation time will be extremely large. So somehow we have to come up with a combined model, aggregated model. And again, there are many approaches in doing that, but to my knowledge, there is not an established one. So that's an interesting topic as well. And another topic that I really started to appreciate much in the last few months is how to model propagation of harmonics in the network. So propagation of harmonics is an interesting topic because it's really difficult to model the frequency response of the system for higher frequencies. Fundamental frequency, the models are quite straightforward. We generally know quite well R, L, and C for components such as cables, transformers, and so on. But at higher frequencies, then some phenomena such as skin effect is coming to play. So, and the other thing is that with increasing frequencies, the models needs to take into account other parameters such as stray capacitances of transformers. So it becomes quite complex then to be able to define models for higher harmonic orders. And the problem is also how to validate these models. How do we know that the system frequency response is what we assume? And so this is a very interesting topic as well. And more recently, I started to work on voltage imbalance because, as I said earlier, this is a growing research area. And voltage imbalance has also an effect on harmonic generation by three-phase inverters. So now I will move swiftly to my research projects. So I will start with one project that's called harmonic mitigation that is funded by Ofgem. Probably everyone on the meeting knows that Ofgem is the government regulator for gas and electricity markets in GB. And I'm working on this project with Western Power Distribution. The project started about a year ago and will end in December 2021. The aim of the project is to assess the impact of using existing PV inverters as active filters to mitigate harmonics level on the distribution system. The project will be principally developed by modeling, but we will also do some lab-based hardware testing. So the project is structured in 4 work packages. The first work package is a literature review and system model that has been completed. So for this project, we are studying a portion of the Western Power Distribution network, and I will show the system overview in the next slide. Now we are currently working on active filter development for a single inverter. And then the next work package will be active filter development for multiple inverters and some hardware in the lab testing. And here I have a link about the project, so you can check more updated information there. As I mentioned earlier, for this project, we are studying a part of the Western Power Network. So in this network, essentially, we have a main bus bar at 33 kilovolt, and then we have the supply at 132 kilovolt, and I think it's 11 bus bars at 11 kilovolt. And in this network, there are 3 PV farms connected to the 30. So in the next slide, I'm presenting active filter operation. So I mentioned earlier that this project is dealing with the studying active filter operation provided by existing inverters. Active filters have been around about maybe 30 years now. I'm not sure if you heard of them or if you are more familiar with passive filters. But in general, active filters in principle are power electronics converters that are controlled in a way to inject harmonic currents with the aim of cancelling existing harmonic components on the power grid. So this is shown in a nutshell in this vector diagram for the fifth harmonic component. So in this case, we start with the fifth harmonic load current that's indicated by this phasor. And then the inverter is controlled to inject a current that's opposite in phase with the same magnitude. And ideally, these 2 components will add up in a way to cancel completely the current upstream the inverter. In this picture, deliberately, I show that there is some residual current just because in the practice, it's very difficult to cancel exactly existing harmonics, mostly because harmonic currents in the system keep changing in time, they're not constant. But as I said earlier, the standards do not generally require complete absence of any disturbance. So if we are left with the small fifth harmonic components, that is acceptable. For the case of this project, the idea is to use active filters as ancillary service. One of the reasons why active filters are not widely deployed, in particular at the distribution system, is because they are too expensive. So it's possible, instead of building a dedicated active filter, to add this function to an existing inverter. And this is what we want to do with this project. And this type of behavior is very simplistically shown in this figure, where essentially I show the PV inverter and the connection to the main grid. And the inverter is controlled to inject fundamental current as well as harmonic currents. Another element to take into account is that when harmonic currents are injected by the inverter, in addition to the fundamental components, there is a concern that the ratings of the devices, of all devices connected in the system, may be exceeded. So we need to ensure that harmonic injected are within acceptable levels. And this is why we are adding to the algorithm an harmonic gain to ensure this level of control and supervision. We are still testing the algorithm, so I cannot really share many results at the moment. I just showed this spectrum to illustrate the behavior. This is a particular case where PV inverter generation and load are constant. And the load include the 5th, 7, 11, and 13 component. So that's the spectrum of the load current, sort of the feeder current. And then after the inverter is acting as active filter, the feeder current presents much reduced level of harmonics. The next step is continue the validation of this algorithm, in particular looking into dynamic operation. And then we also want to validate the operation of the algorithm using a dynamic simulation based on system data recorded in October 2019. The next project is, the title is Impact of Renewable Energy Sources on Harmonic Levels in the Future UK Power Grid, Modeling, Assessment and Mitigating Solution. This is a 2-year project funded by EPSRC. The project partners are listed here, and there are also their logo shown. The project started about 3 months ago, so I don't have really a lot of updates on this project, but I can share, the aim and what we are working on at the moment. So the aim is to study the impact of harmonics generated by renewable energy sources and HVDC on the UK transmission and distribution system. And in particular, what we are looking into is the transfer of harmonics between various voltage levels. This project is divided in 3 work packages. One is model development, the second is harmonic analysis, and the last one is assessment of impact. And this structure is very typical for harmonic studies. So at the moment, we are working on work package 1 because we just started. So National Grid provided us a model of the UK, or better of England and Wales transmission system. Working with that model was not feasible because the model is very large. So we developed a reduced network model. And we were able to find information and data on renewable energy sources at the distribution system level. So we added those to the model at 132 kV and 33 kV voltage levels. And then we collected harmonic data. So the next slide shows the single line diagram of the system. So this is the system we are looking into. And as you can see, the bus bar and lines shown here are mostly at the 400 kV system level, just because we didn't want to make the diagram too crowded. But you can see that there are some interesting connections here, such as HVDC, wind farms, another HVDC here. So we look forward then to the next step, that is to add harmonic generation associated to each source. So the next step will be to add these harmonic sources into the model. And in order to validate this model, we will compare the harmonic levels with the ones provided by National Grid. So once we will have this baseline model, then we will be able to study more, a large number of combination of harmonic injection, because as I said earlier, harmonic injection changes in time, and in particular to forecast harmonic levels in the future. As I said earlier, I started recently to look into voltage imbalance compensation. For voltage imbalance compensation, we are using a similar approach as active filtering. So the aim of this project, of this research, is to see how single phase connected battery energy storage system can help compensate voltage imbalance. In this case, at the moment, we are using the IEEE 13 bus system because this system has unbalanced conditions, so it's ideal for our work. And we are studying the connection of 3 single-phase batteries to the feeder. And the idea is that these units are controlled to compensate unbalance in the feeder. And I don't have much time to explain these results, but I just want to show the effect of voltage imbalance mitigation. So at the top, we have current in the distribution transformer. So what we can see here is that at 1 second, the loads are connected, and we have unbalanced current in the transformer, and it's quite visible. At 2, the inverters are connected. So what's going to happen is that the inverter will generate currents to cancel the ones produced by the loads. Therefore, the transformer loading will decrease. And the last graph shows the voltage imbalance factor that's defined according to IEEE and IEEE standards. So the voltage imbalance factor is essentially a number, a coefficient that explains unbalance in the system. So you can see that at 1, this coefficient jumps from 0 to 3. And then at 2, when the inverters are connected, it decreases to 0. My student will present a paper based on this work at ISGT next month, so that paper contains more detail. Another topic I started to look into recently is related to DC microgrids. DC microgrids are becoming more popular because a lot of the novel power electronic-based devices include the DC stage. So it makes sense to avoid continuous DC to AC conversion, but just try to operate a system with a single DC bus. So we designed a PV-fed DC bus EV charging station. And for me, from my perspective, this topic is quite interesting, again, from a power quality point of view, because there are no specific standards, at least to my knowledge, dealing with the power quality in DC grids. So I think this is a very interesting topic. An overview of the microgrid is shown here. More details can be found in this paper that was presented last year at ICON. So this microgrid includes PV panel, energy storage, and electric vehicles. The energy storage is used to regulate the bus voltage, and an additional group control is used to guarantee safe system operation during demanding system conditions, such as fast irradiance change and low battery charge. I just want to show a couple of waveforms on this. So this graph shows a variation in the current produced by the PV panels. So in this case, two PV panels produce constant current. And then in this case, there is a decrease of irradiance for one of the panels. So the current decreases to 0. This oscillation starts here around 4 seconds because at this point in time, the energy storage starts to inject power to supply EVs. So there is a change in the energy storage operating condition. And this graph at the bottom shows the current going to the electric vehicles. So initially, this graph indicates that the electric vehicles are connected. Some of them draw more current than others. But then when irradiance decreases, two of the electric vehicles are disconnected because there is not enough power supply from the PV and the energy storage. The voltage at the DC bus is shown here. So you can see when there is a reverse power flow from the battery, this voltage is more oscillatory. And in this figure, we overlap the plus minus 5% limits. That's what is in the power quality standards. And this is quite common worldwide. And you can see that the voltage stays within these limits, except for a very short time here. However, this is really a assumption translated from the AC grid standards. They're not really specific to DC standards. This other graph shows the current from the battery. So you see at 4, it becomes negative. And this shows the battery state of charge. I also want to mention very quickly 2 interdisciplinary projects, just because I think this may be interesting for the students or early career researchers. What I've been told by different people in the university and outside is that while it's good to have a core research where where we can specialize, it's also very important to broaden our horizons and try to do more interdisciplinary research. So I started to look into application of deep learning on power quality. And when doing this, it's very important to find experts in those areas. So at the moment, I'm collaborating with a colleague who is an expert in this topic. And essentially, the aim of this research is to look into using neural network to identify power quality disturbances. We took power quality data from PCube. So these are data that are available to everyone. So it can be downloaded from a website. And we used the pre-trained convolutional neural network that needed to be modified for power quality assessment. And I can show you some results here. So essentially what happened is that we feed this type of waveform to the neural network, in this case ResNet, and the neural network associates a label to those. So in this case, the only 2 labels available are normal and abnormal. And then the network associates a level of confidence or accuracy to these results. So in this case, you can see, for example, that the result is normal with a high level of accuracy. In this case, again, these waveforms are abnormal and the accuracy is still quite high. Then we already went to the next step, that is to differentiate between different disturbances. So for example, this will be classified as an interruption. This one has a voltage sag, and this one probably has voltage sag, although there are some harmonics as well. The other interdisciplinary topic I just want to mention is studying of tidal energy integration and power quality. In particular, in the UK, this is an interesting topic given the large tides that take place every day, twice a day. And the purpose of this research was to see how tidal energy impacts power quality. So this was not really related so much to the forecasting of the resources or to the question of matching demand and response or energy storage. Was mostly to see if turbulences in tidal ways would be translated into power quality concerns. We took measurements from a turbine, tidal turbine that was installed in Scotland, and essentially we did analysis on this data. And the conclusion was that the turbulences in tidal energy are relatively small compared, for example, to turbulences in wind, and they take place on a larger time range. So as a result, the power quality from these devices is higher than other renewable resources. So you can see in this case that this is the voltage THD is very small. The top graph shows variation of power, and you can see this is a very typical profile for a tidal turbine. So you can see that the generation takes place when the tides are growing or when the tides are decreasing. And then you have a gap in between. So I just want to conclude then with this slide. So the harmonic impact of renewable energy sources is becoming more visible, and it's a growing research area. These technologies are responsible for introducing power quality disturbances, but it's important to note that they can also be deployed to cancel harmonics on the system, or more in general, they can be deployed to mitigate disturbances, power or other type of power quality disturbances, such as, for example, voltage unbalance. And the other thing is that various new tools can be deployed. So in addition to traditional modeling or traditional signal analysis technique, the use of machine learning is currently considered. I also have a final slide where I want to thank my team, because obviously I didn't do all of this by myself, and I brought the name together with their contribution to this presentation. So with this, I ended my slide, so I think I can give back control to the host of the presentation.
Thank you, Grazia. So with that, we'd like to open up for questions. Just a reminder, if you do have a question, if you could type that question into the Q&A functionality there, and we'll be able to see that. Now, while we're waiting for some questions to come in, I did have one question on the beginning, the first of the research areas that you mentioned. You talked about the reason why PV filter, PV aren't being used as active filters today, related to some of the economic concerns. And I didn't know if you had any initial findings on at what price point it might be economically beneficial for that, for those PV inverters to be used in that fashion, or if you could speak to that a little bit.
Yeah, sorry, maybe I was not clear in when I presented. So, so the economic problem here is that active filter per se, so dedicated active filters are very expensive. So obviously the cost depends on the voltage rating and depends on the size of the filter. And actually, as part of this project with WPD, as part of the literature review, there was some cost analysis that indicated that active filters are quite expensive. And especially, if you need to buy a dedicated device, it will make more economical sense to buy a passive filter, because passive filter is like 10 times cheaper. So in that website I showed earlier here, let's see if I can go back to it. There should be the report that includes some of the costs. Now I don't remember because we did this a while ago. So that has been always a problem with active filters, and even today at distribution system level, they don't, don't make economical sense. So the idea of this project will be that we could use a PV inverter that is being already deployed or will be deployed in the future, and we add this control functionality. So the development of the control functionality will have a cost, probably some software costs, but obviously it's much less than building a dedicated device. And that's what we also showed in the literature review. Part of the motivation is that the cost will be minimal, and probably it will be cheaper than installing a dedicated filter. So I hope that clarifies a bit.
Yes, thank you. I was curious as to what some of those trade-offs were, so that's very helpful.
Yeah, sorry, I don't remember the cost, but it was a while ago we did that report. But I can also follow up later by email on that.
It looks like we have a question that's come in from Helena. The question says, hello, I'm interested in how much research in the power quality area is considering the effective demand response, i.e. changes in the amount and composition of load on power quality indicators.
Yeah, so I'm not working much in that area. So for me, I don't think I can comment much because I don't know much of that. We will include some of this into the IEEE SRC project because part of the project will include assessing the impact of varying number of distributed resources and varying demand. But it's not something I've done so far, so I'm afraid I cannot really comment much on that.
Do have one other question while we're waiting. So you mentioned the evolution of power quality that you've seen during your time in this research area, as well as the problems originating back to the inception of power systems. What do you see kind of as the transition in power quality concerns over, say, the next 10 years, as there's transitions to lower carbon systems and other additional penetration of such power electronics?
Yeah, I think, one area that will probably keep growing, as I said earlier, is the topic of superharmonics, because this is an area that's just started. And there are some already reported issues in the area, but I think when people will start to look more into that, they will find out that the problem is more widespread than what they think. I also think that it will be interesting for me to see what is going to be power quality issues in microgrids, because or in a system with low inertia, because what I've not seen yet is really studying specifically the impact of reduced inertia on power quality. So I think because of the way the system are changing, so reduced number of traditional generation or increase in microgrids, I think the effect of microgrid on power quality would be interesting. So I can see these two as main area at the moment.
Hi, I also have a question about the size of inverter. So in order to use PV inverters for ancillary services, what do you think is the reasonable capacity that we're looking at in terms of the inverter itself?
Yeah, thank you for the question. So I touched on that briefly earlier. So for example, for this project, the inverters consider that are the inverters installed change in size, because every PV farm has a different inverter. So at the moment, we are looking into 500 kilowatt inverter. So we are limited by that rating. So in a sense, if the inverter is operating at full power, 500 kilowatt, we really cannot inject much harmonics. And because this project is looking into deploying active filters in an existing inverter, we really cannot do too much in terms of harmonic injection. But obviously, if we need to start from scratch, we could assume, for example, 500 kilowatt is the baseline power coming from PV. And then based on the harmonic levels on the system, we could increase the rating so that we could inject more. So in a design stage, I think there is freedom to change the rating based on the required harmonics or other ancillary services. However, another problem is that then we need to take into account the rest of the system. So as you know, THD or is limited to 5%. So, for example, if we inject harmonics from the inverter at the PCC, the distortion will be higher. So there is going to be a trade-off between how much harmonics the inverter can inject and then how much the system can take. So I think realistically, we could add maybe 5 to 10% to the inverter rating, you know, but then trying to inject more harmonics will have some detrimental effects on the system.
Thank you much.
Welcome.
Looks like we have another question in the queue. Oh, looks like we have another question in the queue from Rohan. It says, using inverters for active filtering is very interesting. Do you know if wind turbine manufacturers are researching this to use the inverters across a wind farm to cancel out each other's harmonic contribution?
Yeah, thank you for the question. So actually, I did some work on active filtering for wind farms in my PhD. So that's really where my interest in this topic came from. I think this has been studied, and again, the literature review we did last year for Western Power covered existing applications. So I'm pretty sure there were some examples of wind turbines doing that. So for sure, I think you can find examples of application on active filtering for wind turbines. I'm not sure about the technology deployment stage of that, if that's the research stage has been deployed. So that I'm not sure. I think from the research we did, we could see some experimental work, but not actual field measurements. But maybe now that has changed. However, I think the general application of this is not really cancel out each other harmonics, but mostly cancel harmonics coming from the loads, so existing harmonics on the system. So in terms of canceling each other harmonics, I don't think that has been done. Because I think it would be a challenge, you know, to have the measurement points, because you really cannot monitor all harmonics from all the wind turbines. So what I know, the typical application is to cancel harmonics outside the wind farm.
It looks like those are all the questions in the queue. So at this point, I want to thank you so much for the wonderful presentation, and would like to thank our audience as well as the IEEE for sponsoring this event. Thank you so much for your presentation, and look forward to the research to come and the culmination of these projects.
Thank you very much. Thank you. I just realized I don't have my email on the slides. But I think you can find me easily with the Google search. So if there are more questions, I'm happy to answer afterwards.
And also one final thing, we'll be sending out in the chat, there should be the link to a Microsoft Office survey that will be, we'd appreciate if you would fill out for all the participants, so we could get a feel for future events that you might be interested in, as well as whether you're an IEEE member or not. That would help us a lot for improving the events that we host in the future. Great, well, thank you so much.
Thank you again. Bye.